This video explains race conditions in data races and provides strategies for detecting and avoiding them in Go. The content is focused on understanding concurrent programming challenges. This is all about Go concurrency. A race condition occurs when multiple Go routines, which are lightweight, concurrent functions in Go, access shared data at the same time. The program's behavior then depends on the order in which each Go routine executes. Here's a simple example. We define a variable called counter as an integer. The function increment increases the counter by 1. The counter increment operation is non-atomic. When multiple Go routines call the increment function, a race condition can occur. Here is a demonstration of a race condition. Suppose you have a bank balance initialized to 1,000. A withdraw function checks if the balance is greater than or equal to the amount to withdraw. If it is, it subtracts the amount from the balance. Now, imagine that two Go routines call the withdraw function at the same time, both trying to withdraw 600. The expected outcome is either the balance is 400 or the balance is 1,000, depending on which withdrawal happens first. But, due to the race condition, the actual balance could be negative 200. This happens because both Go routines might see the balance as 1,000, and both subtract 600, leading to an incorrect final balance. It is important to distinguish between a data race and a race condition. A data race occurs when there is a memory access conflict without proper synchronization. It involves simultaneous access to the same memory location, with at least one operation being a write, and no mechanisms in place to synchronize these accesses. This leads to undefined behavior. A race condition, on the other hand, is when the program's output depends on the timing and sequence of events. This results in timing-dependent behavior and non-deterministic results. A race condition is a logic-level problem and can exist even when synchronization mechanisms are in place. Go provides a built-in race detector, which is a powerful tool that can identify data races at runtime. It dynamically detects races during program execution and provides detailed reports about where these races occur in the code. To use it, you can add the race flag to the Go run, Go test, or Go build commands. For example, to check for races when running your main program, you would use the command go run-race main.go. To check for races during testing, use go test-race /. And to include race detection in your compiled binary, use go build-race main.go. Here is what the output from the race detector looks like. The race detector output shows the exact memory address where the conflict occurs. It identifies the conflicting Go routines involved in the race. It provides the file name and line number where the race is happening. It also shows the stack trace of where the Go routine was created, which is very helpful in debugging. The example output shows a warning that a data race was detected, the location of the write operation, the previous read operation, and the Go routine that triggered the race. There are several strategies to avoid data races and race conditions in Go. The main approaches include the use of mutex locks, channels, and atomic operations. Mutex locks synchronize access to shared resources, ensuring that only one Go routine can access a particular section of code at a time. Channels enable communication between Go routines by sharing memory, which helps to avoid direct access to shared variables. Atomic operations are lock-free synchronization primitives that provide atomic reads and writes, ensuring that operations are performed as a single indivisible unit. In this example, the mutex lock is used to protect the counter variable when incrementing it. Here is a summary of best practices for preventing race conditions and data races in Go. Always test your code with the -race flag to detect data races during testing. Use synchronization primitives like mutexes to protect shared resources. Prefer channels for communication between Go routines to avoid direct memory sharing. Consider atomic operations for simple lock-free synchronization. And design your concurrent programs with safety in mind from the start. Remember, prevention is better than detection. Don't communicate by sharing memory. Share memory by communicating. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.